everyone uses smartphones, right? We have functions like GPS, camera, speakers, Bluetooth, and Wi Fi, and many more things inside. But what exactly makes all this work? The reason for all this comes from the motherboard and the chipset within the phone and the way it is configured to bring a smooth experience for the user. Likewise, the properties of compounds and atoms in chemistry are explained using the understanding of electronic configuration of elements. The electronic configuration represents how the electrons are distributed in its atom among the orbits or shells and subshells. We have already discussed about the three main principles, which are Aufbau's principle, Pauli's exclusion theory, and Hund's rule of maximum multiplicity. But how to use these principles for the distribution of electrons in orbitals? Let's discuss about that. We will start with the ways to represent the electronic configuration of atoms. It can be represented by using either S raised to A, P raised to B, D raised to C, F raised to E notation, or through an orbital diagram. First, we will discuss this S raised to A, P raised to B, D raised to C, F raised to E representation, which is called notation. Here, the subshell is represented by the letter symbols S, P, D, F, etc. and the number of electrons in the subshells are represented by the letters A, B, C, D, etc. In case of similar subshell, they are differentiated by the principal quantum numbers. For example, the electronic configuration of lithium is 1s2, 2s1. Here two similar subshells, that is S, is differentiated by principal quantum number or orbital number 1 and 2 respectively. The second way is the orbital diagram. In this notation, each orbital in the subshell is represented by a box and the electron is represented by an arrow. The arrow in the upward direction represents a positive spin and the arrow in the downward direction represents a negative spin. Let us understand the electronic configuration with an example. The first example we will take is hydrogen, which has an atomic number of 1. So the electronic configuration of hydrogen will be 1s1 and the orbital diagram is mentioned here with one positive spin electron in the S subshell. The second is helium with an electronic configuration of 1s2 and 2 electrons with opposite spin is filled in the S subshell. Let's discuss few more examples of electronic configuration. Here, the third electron of lithium is not allowed in the 1s orbital because of the Pauli's exclusion principle. So, it takes the next available choice, that is 2s orbital. The electronic configuration is 1s2, 2s1. The 2s orbital can accommodate one more electron. So, the electronic configuration of the next element, beryllium, is 1s2, 2s2. In the next 6 elements, that is boron, carbon, nitrogen, oxygen, fluorine and neon, the orbitals are progressively filled. If you look at the nitrogen, you can see that all the p orbitals are singly occupied and only then the electrons with opposite spin is filled for oxygen, fluorine and neon. The electronic configurations of the elements like sodium to argon follows exactly the same pattern as the elements from lithium to neon with 3s and 3p orbitals as studied in the previous slide. This process can be simplified if you represent the electrons of the first two shells by the name of the element neon, that is 1s2, 2s2, 2p6. Now, can you see a new pattern in the electronic configuration? Here 3d orbitals have lower energy than 4p orbital and that's why it is filled first. In these 10 elements, the 5 3d orbitals are progressively filled. But did you notice that chromium and copper have 5 electrons and 10 electrons in its valence shell rather than 4 and 9? Chromium, whose atomic number is 24. So, according to the normal configuration we have studied, it would have been 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. But this configuration is incorrect. The correct configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. The reason being the extra stability of the fully filled and half-filled orbitals. Here, the ground rules for writing the electronic configuration of elements always correspond to the state of lowest electronic energy. But like chromium, we have exceptions as well. These exceptions are because of the shift of electrons from subshell of lower energy to a subshell of higher energy. This leads to the higher energy orbital to be completely filled or half filled for more stability. In the case of copper with atomic number 29, the more stable electronic configuration will be d subshell completely filled and s subshell half filled rather than d subshell with 9 electrons and s subshell completely filled. Now, let's discuss the reasons for extra stability of completely filled and half filled subshells. In these cases, as you can see here, electrons are symmetrically distributed in the orbitals, and so they have same energy but different spatial distribution. In this, the electrons are more strongly attracted by the nucleus. Here, let us talk about the exchange energy in d subshell. The maximum number of electrons filled in it can be 10. First, we will discuss about the exchange energy in half-filled d subshell. Here, the first electron can exchange its energy with the next 4 electrons. So, the exchange energy becomes 4. The second electron can exchange its energy with 3 electrons. So, the energy becomes 3. Third electron can exchange its energy with 2 electrons. So, the energy becomes 2. Likewise, fourth electron can exchange its energy with 1 electron. So, the energy becomes 1. Total exchange energy in half-filled d subshell becomes 4 plus 3 plus 2 plus 1, which is equal to 10. In a fully filled d subshell, the exchange energy will be double compared to the half-filled d subshell. So, the energy exchange in a fully filled d subshell will be 20. That's why the half-filled and completely filled electrons are more stable. Here, the most important thing to note is that the exchange in energies happens in between the electrons having same spin. Now, based on the learnings of electronic configuration stability, try to find the answer of the question: why elements like helium and argon are not reactive, but elements like halogens are reactive? Well, try to figure out the answer. With this, let's summarize what we have learned.
Manorama Horizon. Learning made simple.